I'm Adam Young, and they've once again broken the don't give Adam Young a microphone rule. We are here to talk about JWS tokens, JSON Web Tokens. And so we wanted to give you a sense of why we're talking about this, and why are we doing yet something new here. And we banged this back and forth, and we figured this is kind of our mission statement. Imagine if, instead of what we have today, we had a token format, a token that is compatible still with OpenStack. We don't want to break things, but with everything else as well. And so with that as our guiding theme, we're going to go through.
Yeah, so this presentation actually follows a similar template to other presentations that we've had in the past that introduce different token formats. So we're going to try and keep as much of the redundant content as minimum as possible so we can get into some of the reasons why JWS is important for us. But we're going to introduce what a token is. We'll also walk through some of the historical context behind various token formats, and that sets up the stage for why JWT and JWS are important for us today. We'll also compare the two token providers that we support, Fernet and JWS. We'll tell you how you can get things configured. And then we'll go through some notes about key rotation and distribution, so things that you would do on day 0 and then day 1 and day 2. Then we'll kind of talk about some of the doors that this opens for us in the future. We should have plenty of time at the end for some questions if you have any.
And if not, then some music. Okay, what is a token? If you do any operation in OpenStack, say using the CLI, the very first thing it's going to do is go to Keystone, get a token, and then it's going to be passed. In this case, it's the user is doing something against the server's API, a Nova call. And you can see that at the bottom we have XAuth token, $ token. So the assumption is that in an earlier stage, you fetched this token and got it and stuck it into an environment variable. The tokens are if you look at the token design pattern, if you look at like the Gang of 4 books about design patterns, a token is really a remote pointer. It's a way of pointing at some remote data. Now, it's used in security contexts a lot to point to specifically remote data about access control, authentication, authorization. And that's definitely the case in Keystone and in OpenStack in general. So when we're talking about tokens, we are talking about the access control tokens that are issued by Keystone when talking to Nova, Glance, and so forth. And there have been several different token formats over the years, and they all have had reasons. They've all had shortcomings, and there's a reason why we're continuing to evolve them. I've been around the project since 2011, so I've been through all these different phases, including making some of the mistakes that we're going to talk about here. And so we're going to provide a little bit of historical context why we're where we're at, because it helps set up for what we're doing. A UUID is a random number. It's a random number that is then put into a string format, so it's a little bit easier to use. And this is the first format of token. Now, with a UUID like this, with a random number like this, what you have to do is you have to take the data that you're associating with it and persist it somewhere, because there's absolutely no information in this other than the data that you see here. So 7798 doesn't mean anything. If you hand this back to Keystone, Keystone can pull out of its persisted database the blob. It was a serialized JSON block that has the username, user ID, the roles, the project, all associated with that token. And so we had to persist the data, which means if you want to spread this geographically, you have to synchronize the databases between different locations. You also have to periodically flush the data that's in there or make sure it's expunged, or you're going to fill up your disk. Is that everything we got? You want to talk about there? And actually what we found is places that didn't do this would actually, even in a quiet cluster, would eventually fill up their disks and come slower and slower because of these problems. So Terry's here. In a conversation, I want to say it was in San Diego, he mentioned to me that Keystone is the chattiest part of OpenStack. I said, well, it doesn't have to be. He's like, really? So that led to a whole development effort of trying to make the token contain the data that we were talking about persisting before. So we took the result of doing a token validation, put it into a document, signed that document using crypto message syntax, and that's what you see here. This big block, which this was actually a shorter one. We pulled the service catalog out of this. They could be huge. And that was the problem. That was really the critical failing of PKI tokens, was what they were huge, but they had all the data in there, and they used PKI. Now, what is PKI? Public key infrastructure. It is a way of doing asymmetric cryptography using X509 certificates. And why? Because that's what we had at the time. You know, we forget that a lot of the tools we take for granted nowadays didn't necessarily exist at the time we were making these decisions. One of the big ones that's come up is the Python support for cryptography. And back then, we were using what was called greenlets. These are not really threads. It was the Python way of trying to do threading in userland. And it meant that if we did some long cryptographic operation, like signing, the whole web server would stop. So we had a lot of things we were working around, and PKI had failings because of those. But there were promises there. One of the first things we did to try to deal with the huge thing is compress them before we did. Well, this is a different token format, and so we have PKI-Z, but they were still too big. And they still had all those problems with key rotation and key distribution, and thus we needed something that would work. One of the big problems with them being so big is if you're fronting your web service, like Keystone, with Apache, you only have so much space in the headers. There was an 8K boundary, which with the service catalog, we would blow out. And thus, we had failures. You strip the service catalog out, we compressed and all that, but we still found that they were too big. So we went to Fernet. This is still me, right? Mm-hmm. Okay, so Fernet was an attempt to maintain the stateless aspect of the tokens. Because with PKI and PKI-Z, you no longer had to persist it to a database. Now, we had revocations, which did have to be persisted, but we'll ignore that for the moment. Fernet was an attempt to get a minimal amount of data into the token body such that Keystone itself could encrypt and decrypt it, and only Keystone. Keystone used symmetric cryptography to sign the token. So this was opaque. Nobody could read the data that's inside this little blob that you see in front of you, but Keystone. Keystone would take the blob back, decrypt it, and there was only a minimal amount of information there. We didn't have the whole service catalog. We had the user ID, but not the username. We had the project. We did not have the role assignments in there. And thus, and there were a couple variations on that. We had a special format for trust and stuff like that. But in general, they were very small. I believe we were able to keep them under that magic boundary that the database liked for a string, that we could still index on them. And so that's what you see here. This is an example of that. It's in a message, a very concise binary message syntax underneath there, and then signed. So why not stick with Fernet tokens? Well, partially is because as much as we talk about cryptography and we use it, Keystone developers and the people who use Keystone are not cryptographers. We are not people maintaining cryptographic libraries, nor should we. The Fernet, one of the big things is that the Fernet phase is kind of come and gone, and it's not really being super supported anywhere. It's not being used that much anywhere but in Keystone. And that was a warning sign. There's also scalability issues with using the symmetric signing and database thing. So we want to see if we can get something that's a little bit more forward thinking. But the big thing here is, if we go back to that initial vision, is like, can we get something? Now we have trouble with Fernet, we want to move forward. Can we get to something that's more of a standard? And again, just like cryptography didn't exist way back then, the standard that we're about to talk about did not exist way back then. Now we got something next, something new.
All right, so that kind of sets the stage for some of the advantages that we get with JWT and JWS. But first, what is a JSON Web Token? How many people here are familiar with JWT or JWS?
Okay, good.
Some hands.
Good.
It's really an open standard for sharing claims between parties. And in Keystone, we're using that for authorization information. But more specifically, it's actually detailed in RFC 7519. So if you want more information on it, that's a great place to start. But there are other specs that actually detail important things about the JWT ecosystem as well. RFC 7515 goes into JWS, which is JSON Web Signature. RFC 7516 goes into JWE, which is JSON Web Encryption. And the last one, RFC 7518, goes into JSON Web Algorithms, which are the algorithms used throughout that ecosystem. But really what JWT gives you is a way to define a set of public claims, so things that are standard across many different token formats used in the industry. The big thing that you need to know right now is just that JWE and JWS are really a subset of a JWT. The implementations also are allowed to support private claims, so if you need more information in that token, you're allowed to extend it in a way. They support signed and encrypted payloads, and they're built using asymmetric cryptography. So this is what a JWT looks like. They're still relatively small. They're not quite as compact as a Fernet token, but they're still very copy-pastable. They're still non-persistent. We have no intention of writing them anywhere. They're built using asymmetric signing, and they do require some sort of online setup. They don't work out of the box like UUID tokens did, but you need to set up Keystone with a public-private key pair in order to issue and validate tokens. And then finally, they do require online validation. So while the underlying implementation is built using asymmetric signing, which leads itself to offline validation techniques, we don't really put enough information in the token itself for that to be useful at a service. For example, role information, we don't put in the token payload, which kind of makes the token a little useless when Nova gets it and tries to see if the user can do something or can't do something. So for the time being, you still require that round trip back to Keystone in order to perform that validation. So let's deconstruct one. JWTs are really three different parts. They consist of a header, a payload, and a signature, and the first part is the header. The rest of that token really isn't showing up here, but headers really just consist of metadata. So they consist of an algorithm and a type. For our purposes here today, the algorithm is going to be ES256, and the type is going to be JWT. This is what you're going to see from Keystone in the immediate future. Next is the payload. This is really where all of the token claims live. And this is an example of what it looks like. Here you can kind of see a mix between the public claims as well as the private claims. And then finally, we have the JWT signature. So this is how we integrity verify the contents of the token. And this is built by taking the header and the payload, encoding those two pieces of information, and then running it through a SHA-256 HMAC. And then that's tacked on to the end of the token. So let's talk a little bit more about the public claims. Again, these are defined in RFC 7519. So they're very common things. There's a principal, which in our case is the user of the token. So as you generate a token, you're going to be referred to as the subject. We also use a public claim for expiration time as well as issued at times. But that's not really enough for us to rebuild an entire token response just based on those three pieces of information, which is where we use private claims. So private claims is what we use for token scope. When you get a token scope to a project, a domain, or the system, we relay that information in a private claim. We also use private claims for auditing information and your authentication methods. So whatever you, what methods you use to obtain that token. So now I'm going to let Adam compare the two different approaches that we have today.
Okay, so both Fernet and our existing implementation of JWS, JWT, are going to support non-persistence. You do not need the validation data, the data that comes back from a validation request, stored in the database. And we're still doing online validation. That's to keep the token size small. We're a little worried, again, if we start packing more and more data into the token, that they are going to expand inside, explode inside. So let's get the standard out there. Let's get people using it. Let's work through the issues of key distribution and all that kind of stuff. Let's change one thing at a time. And the only thing that we want to change is from Fernet to JWS. So still online validation. Opacity. We talked about how in a UUID token there's no information. In a Fernet token there's a minimal amount of information. There's a comparable amount of information in the JWS token. And if you know what you're doing, now you can actually extract some of that information. So while the encryption on Fernet means that this information is completely opaque and thus not readable by anybody that has the token, that's no longer the case. We're only doing signature. Again, that keeps the token smaller, but it does mean that if somebody really wanted to take that payload and reverse it, they could see what user had it, what project is in there, and so forth. The reason why the token is larger is primarily due to the asymmetric cryptography, Back when we were looking at Fernet and options there, I did a comparison of encrypting a zero-size message, a message that was basically empty. The Fernet one you saw, that size was around 500 bytes, and I believe the asymmetric one came in just under a K. The numbers might be a little bit off, and there's certain quanta there that if you cross a line, it's going to jump larger. And so we want to try to keep it as small as possible, but the greatest difference in size is due to using asymmetric cryptography. Now, one of the benefits of asymmetric cryptography is it really helps on the key rotation distribution story. Specifically, once you generate a private key, you should never remove that from the system where you generated it. If two things need to be able to validate each other, you share the public keys. And so all we have to distribute now is the public keys, even if we're signing the same set of data. It just means that validation has to go through a distinct set of keys in order to check it, which, by the way, is what Fernet does today to allow key rotation. This is an essential part of key rotation. We'll just have to remove any keys that we no longer want to be able to validate signatures. So from the crypto algorithm standpoint, the Fernet standard uses 128-bit AES CBC encryption, and then a 128-bit SHA-256 HMAC as its signing keys, okay? JWS uses this standard here. I could read it for you, but it's probably easier to read off the stage. The elliptic curve is probably the most interesting thing, and one of the questions we anticipate people asking is, where do these come from? They come from the same underlying library. It basically resolves down to OpenSSL by way of Python cryptography. So these are supported without changing the libraries. And
one other thing to note too, ES256 is the most recommended signing algorithm in RFC 7519, which is a really important thing for us when we first started to look at this implementation.
Which is what I was just about to say, but he was afraid I was going to miss it, but thank you. Okay, so let's talk a little bit about the configuration. As for anything else Keystone-wise, you're going to modify keystone.conf. Under the token subsection, which is a long-standing stanza within the config file, when you say the token provider, which currently would say Fernet, you would change that to JWS. Now we have a new subsection under there too, which is the Jwt Tokens subsection. And you say JWS public key repository and private key repository to specify those two files. And just like you would with protecting your key pair for SSH, you want to make sure that while the world might be able to read the public key, that private key repository should only be readable by, in this case, the WSGI user Keystone. Assuming that you're running such, Apache in the front, the Apache user does its stuff. This is actually the WSGI user in the back end should be the only system user that's able to read that repository. You're going to have a couple of files that hold that public and private key. So that private one is the one I was just talking about. You want to have probably Chmod 600 on it.
All right, so now we can kind of step through some examples and then some things about key rotation and key distribution. You do need a key pair. It's mandatory. We do provide a utility for you to generate your own using Keystone Manage, but it is opinionated. It's going to generate an ECDSA key pair using the NIST P256 curve. If you want to generate one with a different curve, you're on the hook to do it. And regardless of generating it with Keystone Manage or on your own, you're going to have to point Keystone to those configs like Adam was saying. Key repositories are still on disk. Every API server needs its own public-private key pair, and Keystone Manage does not handle rotation. With asymmetric signing, we don't really need a use case for rotation like we did with maintaining a set of shared secrets like we did with Fernet. So let's walk through an example. This cluster, assume, isn't actually responding to users. This is all before we actually expose them. And you can initiate this from any node. We're just going to start with node 1. But our first step is to create a key pair. So this is going to generate pub1 and priv1 on node 1. And then our next step is to distribute that out to node 2 and node 3. We're going to repeat that process on node 2, generating a second key pair, but only propagating out the public key. And then finally, we're going to do node 3. So then at this point, everyone has the same public key repository. So essentially, a token issued from any node is validatable on another node. And we just want to make sure that you're specifying the proper paths in your Keystone config in order for Keystone to find your private keys and then the public key repository. The important thing to note is that the private key never leaves the host that it was generated for. So you no longer have to sync that secret information across another boundary. So now we're going to talk about some of the things that this opens up for us in the future, some avenues that we have to go down, and some interesting things that we can do with it.
Okay, so we've got a sub-agenda for this section. We're going to talk about doing operations beyond just what you can do with OpenStack. Some of the powers that nested JWT will allow. Talk about offline validation, per domain token signing, and finally, talk about some of the other algorithms that we might support in the future. Probably the first thing we want to do is test with OpenID Connect. We have reason to believe that it will work as an OpenID token because that is relatively forgiving. We're using the right public claims for that. I don't want to say that it will work because we haven't tried it yet, but this is low-hanging fruit. And that means that anything that can do an OpenID Connect token, we should be able to use a Keystone token with. And that opens up the whole web app layer, the whole layers above Nova and so forth. And specifically, we know that Kubernetes uses a JWT style thing. So we're gonna look at again, the public claims and what specific private claims it requires to see if we can provide those perhaps within a single token body and thus have a single token from Keystone that will be used for all the Kubernetes services. And then identify other JWS consumers out there and make sure that we can work with them. That's a prioritization type thing. Feedback certainly wanted on that. And we want to identify other private claims that make sense to have in the tokens. And those two things actually go hand in hand. If there's a consumer, but it needs a specific private claim, but that can map to something that we have in Keystone, how do we do that mapping? And how do we make sure that we don't needlessly expand the tokens? So there's some work to do in there, but it should be a very fruitful exploratory session. We talked a little bit about the ability to encrypt and then sign. This will give you privacy. So this is what nested means. It's the nesting of operations in there. It's important that you encrypt and then you sign. If you do it the other way around, you're signing data and then encrypting it. You basically have to decrypt in order to validate. That doesn't make sense. Once we do allow for this, even though it's going to make the tokens larger, it's going to mean that they're going to be a drop-in replacement for Fernet, which might be essential for certain customers that are passing these tokens around but do not want them. Since this token is typically considered a symmetric share secret, it's probably not a good idea to be passing them to untrusted services, but it's definitely better to have minimal attack surface. So this might be essential. This is what gets me excited. This is the reason I'm standing on stage here, because this was the whole driving thing behind PKI tokens way back when, and it broke my heart, even though it was the right thing to take them out. So I want to get back to that. I want to be able to do offline validation. I want to be able to hand a token over to Nova, and Nova doesn't have to talk to Keystone, except maybe to fetch the service catalog or some subset of the data. That's going to be a larger token format. It's going to need to have all that information. So we have to figure out how to put the roles in there without jumping over those quanta, how to put the right set of data in there without expanding beyond what we're comfortable putting in the token body. And we're going to need to cache some of that information. It might be that if we are doing implied roles, then we want to have the role implication expanded out by Nova and so forth and so on. How do we fetch and keep that stuff in sync? That's a non-trivial problem. That's one of the reasons why we're not doing it yet. If we want to avoid the sins of the past, we have to avoid token revocation. One thing we have now that we did not have then, recurring theme there, is this idea of a service token. When you did a snapshot, Nova needs to talk to Glance, and it uploads the image to Glance. On certain systems, this would take over an hour. And the default token timeout, the expiry was an hour, which means a token issued at the beginning of that operation would not be valid at the end. Well, it turns out it's 2 calls to Glance. It's an upload and then a set some data. And that set data call would fail because it happened over the hour boundary. What you can do now, what Nova will do now, is it passes on its own service token on both those calls. So its service token on that second call would have been refreshed. And thus, when Glance sees the request come in, even though the original user's token has expired, it's going to say, I'm going to treat this as valid because Nova tells me it was valid when the operation started. Once we have that, we can shorten the token lifespan so that we no longer need revocation. Revocation happens if somebody changes a password or something like that. You want to change things immediately, so old tokens out there are no longer valid. Well, if tokens only live 5 minutes, you don't need to revoke them. They will expire before the revocation would have propagated around the system anyway. These are all lessons learned from the past, that if we can handle these now, then we'll be able to get to offline validation. And one of the key use cases that this allows us to consolidate is Keystone to Keystone federation. Has anybody here done K to K? Yeah, see, there's a reason. It's hard. It's SAML, and SAML done in the Python layer, and it really has to be like a first-class citizen in order to get to the scale that we want, where you have all the data in one Keystone server, but you need in another one, but you don't want to do database replication. We did a little bit of back-of-the-envelope calculation, and we realized if you're doing Galera, you can get up to 12 sites. If you're doing HA, that cuts you down to 4 because you have 3 nodes at each site. That's not large enough to get to a setup where you're running a 1 million node data center. You need some way to scale. Keystone to Keystone federation allows us to work towards a scalable solution. We need to make it easier to set up. If we have a common token format between operations and Keystone to Keystone federation, it greatly simplifies the infrastructure, and it hopefully will increase usage of that mechanism. Per domain token signing, this is another scalability thing, but this is looking inside a single cluster. You could actually specify that a given system can only sign 4 tokens for a given domain. And a domain, it's kind of arbitrary, but it's like the right level of scoping. So you could say, hey, all my gold customers, my top tier customers, they're allowed access to this cluster over here. They can also go on the silver and the bronze clusters, but my silver customers can do that, and bronze customers can only do the bronze cluster. So I want to have different systems able to sign for data, and I want a user to be able to say, launch on this availability zone and have Keystone information used to say, yes, they can go there or not. So that means that something has to say that this domain, this token script, this domain, maps to this amount of information. Well, you can do that at the Keystone level. You could have 3 distinct Keystone servers that have, and I talked about this in previous talks, so go back through like Berlin and earlier. But the idea is that you can actually scope down to a given set of machines what the Keystone is able to sign for, and then when you validate the signatures, you would say, oh, that came from a Keystone that is or is not allowed to sign for this set of machines. And also, it'll allow us to consolidate the assignments. Again, this whole idea of trying to keep 2 distinct Keystones in sync, it's hard. We really want to have one view of who can do what within a larger cluster. The other thing that this allows us to do is to perhaps have Keystones at different levels of maturity. And this is somewhat under pro-domain, but this is really something that JWS will allow us to do. And because they're trusting the data in that token as opposed to having to go to Keystone, they could run at different levels. This is something that's going to be essential as we get to 18, 20 distinct Keystone servers running in larger domains. You can't break down your whole cloud to do an upgrade. So we need to make use of these mechanisms to be able to separately upgrade, whether we do the hub first and then the spokes, or all the spokes and then finally the hub, I don't know. We'll work through that, but we need the mechanisms in place, and this is one of the key ones to be able to do that. You want to talk a little bit about the algorithms? I know that that's your thing.
Again, currently we only support ES256. Additional algorithms may come in the future as they make sense, and that's going to allow for better crypto agility. Again, one of the biggest benefits we get out of having a JWS implementation is that we have a backup in the event anything ever goes wrong with Fernet. Granted, there's differences between signing and encryption and the opacity between token formats, but at least it's a step in that direction. A comparable drop-in replacement for Fernet would be ideal, but this at least gets us moving in that direction. And with that, we actually have some time for questions. So if you do have a question, feel free to use the mic in the center of the room. Otherwise, we can repeat it.
It's always scary when there's no questions. It's like,
Hey, which release of OpenStack is this new token format available in?
Stein.
Okay. And
I told you we were
is it
going to get that
be
question.
mandatory at some point?
What's that?
Is it going to be the default token?
I don't think we have any plans to make it the default right now. There's flexibility between it, so we're kind of leaving it up to the operators.
My optimist view is it's going to happen as soon as we have a CVE that we can't address in Fernet.
I'm just going to shout it from here.
Okay.
With Fernet tokens, we had a nice beverage to go with that called Fernet. What beverage do you suggest if we switch to JWS tokens?
Okay, so the question is, what do you drink with JWS? Totally up to you.
Juice.
I mean, a lot of people
Juice.
didn't like Fernet, so they were a little off put by the beverage. So it's your call.
We have a system that does JWS tokens for other parts of the business. Do you see in the future where we could somehow integrate with that? I know that you mentioned something about the token sizes growing abnormally large and all that kind of stuff. If we take their token and decorate it with more, anyway, that's.
I could see doing, so you see how we said token providers, JWS? I could see doing a custom token provider in your case where you're going to pass through to that other one, and then you still would have to query the information. It needs to be in the right format. It might be that you have a custom one that will issue from there, but there's a lot of workflow in there. You need to make sure that you're meeting all the contracts, right? OpenStack CLI is going to go to Keystone to get a token, get that service catalog. You still need to handle all that. Tying in with that, it'd probably be more of a case of making sure that the tokens that you issue in both are compatible to start with. And then, hey, provide the feedback. There might be something that we can do there. That would be wonderful.
Also, tacking on to that too, we spent a ton of time leading up to, I think, the Rocky release where we cleaned up a ton of the token provider API. So point being, it's a lot easier now to write your own token providers. So if you want to take the JWS token provider, extend it, add some more private claims that your other systems know how to understand, then pop them off when they do their validation process, and then just key both clusters with the same keys, then maybe that's an option for you. But it's a lot easier to dig in that code now than it was a year or 2 years ago.
And you could take your other token provider and say, hey, here's additional private claims, the one that Keystone has in there, and see if Keystone will validate. It's going to need to have the data in sync between them one way or the other. But yeah, there's things like that we can do. That's really what we want to start talking about. Uh-oh.
Do you guys have a recommendation on a different curve? Like, say you don't want to have a backdoor key, and will the tool ever support anything other than ECDSA?
So that's a great question. We stick to the underlying PyCA cryptography library, and they support the NIST curves.
Right.
They don't support any of the other curves, unfortunately, and that's a decision that their community will have to make. If that ever gets to that point and they start exposing some other curves, I think it'd be really cool to try and see if we can work some of that in to offer some more flexibility. But for the immediate future, it'll probably be just the NIST P256 curve. And as far as the recommendation goes, I don't know if I'm qualified to recommend another curve outside of what we have relied upon from PyCA cryptography. But great question.
Cool.
Yeah, but as Lance said earlier in the talk, that while Keystone Manage won't do that, generating your own is the same mechanism that you would use to generate that curve, and then providing those two files. So you could generate the one using the standard curve, kill those files, and put your own in place with the same permissions. So you have the same degree, and you could do mix and match if you really decide you wanted to. But it's going to be up to us to push the community to adopt the wider thing. Again, we're not cryptographers, so we have to get the people who care enough about this to get the eyeballs on it. And they're sitting over there, the Barbican folks.
Any other comments, questions, concerns? We'll be around this week, so if you think of something later, feel free to come and approach us. And thanks for coming. We appreciate it.